Welcome to Chapter 14 in our trek through the solar system. A couple of things we're going to cover today are going to be repetitious of last week because we have an overlap with regards to meteorites and meteor showers and stuff like that. So I may gloss over those a little bit quickly because some of the things we've already covered. We have one more chapter after this. Actually, technically, we've got two more, but I put them together. Chapters 15 and 16 are both on the topic of the sun, talking about the surface, talking about the structure under the surface, talking about the effects, talking about gravity and other kinds of things like that. So I put those together into one lecture. Most textbooks actually have one chapter on the sun. Ours has two, but I'm not really sure why they separated it out in the way that they did. So for our purposes, we go back to having one. That means our final week will have an extra credit video. So our final, our 16th meeting, as it were, will in fact be an extra credit video. So watch out for that. In addition to what I'm putting up today for this chapter, I will put up a couple of other extra credit videos as well. So if you watch them and you then talk about them in the discussion board, you'll get some extra credit points. So watch out for that. I won't actually post that up onto anything. What I'll do is I'll just put the discussion board up there. And the way I will know that you watched this video is that you'll say, hey, I want some extra credit points in the discussion board by watching the other videos that I post this week and then talking about them a little bit. Doesn't have to be extensive, just let me know that you watched them and what the topics are and things like that. Without any further ado, let me see if I can figure out the screen sharing thing. They change this around every now and then, and just last night I got another update and saying, oh, well, you need to do this. So we will give that a try, and I want us to go to, there we go, cosmic samples and the origin of the solar system. So a couple of things we're going to cover here include, as I mentioned before, meteorites and meteor showers, because they give us a clue of what was happening in the earlier solar system. We'll also do a brief look at planets, how we can detect planets in other solar systems. So that's a relatively new topic in terms of our progress into astronomy. And hopefully this will actually come up. So we have a little circle going here. I'm not sure what the delay is, since it's not actually having to download anything. And I'm going to sit here. Okay. And it looks like PowerPoint died. Okay. So let's give this another try here. Double clicking. I'm not Microsoft error reporting. Okay. And I'm actually going to stop all of this right now because something is happening. So I want to stop sharing for a moment, and I'm going to pause. Okay, we're going to try again here, and we're going to see if we can get this to share and actually load again, because of course, this is what happens whenever we are running to a deadline. I don't want to stop the meeting. Thank you. So let us try to start the slideshow again and see what happens. Hey, there we go. Ain't technology great? Yes, except when it's not. When we're talking about meteorites, as we mentioned last time, they are the things that land on Earth. In fact, these are part of the leftovers, for the most part, of what our solar system was when it was originally forming, before the sun was there, before the planets were there. So in effect, when we pick up a little meteorite, we are picking up a planetesimal. Planetesimals are the Legos, or the building blocks of the different things that we have to make up planets along the way. Dust and gas particles can coalesce into planetesimals. When we see them entering our atmosphere, quite frequently we have these streaks The streak itself, the sort of shooting star, is neither shooting nor a star. It is a meteor. If it has a particle that lands on the ground, it is a meteorite. Often when we see meteors, we see them coming in as a meteor shower. That's because quite frequently they are in clumps, because most of our meteor showers are leftovers from comets and comet tails that have gone near the Earth. So they all seem to be sort of coming from the same direction, sort of like here. We can sort of see in the distance there. If we were to have a sunset at the end of the railroad tracks here, we might say, oh, well, the train is coming right out of the sun. Well, we know it's not coming right out of the sun, but it's coming out of that direction. So we think about our meteor shower coming from the direction of, say, here's the Big Dipper behind this. So we might call this the Dipper shower. When we have different showers, like the Leonid showers, this one seems to come from the constellation of Leo. We have the Perseid shower, which comes from the constellation of Perseus, or the Geminid shower, which comes from the constellation of Gemini, except they don't really come from those constellations. They are coming from an area that's in front of those constellations. So it's like using a backdrop here, and the constellations provide the backdrop. Some showers are more intense than others, as we see here. Here's a painting. It looks like the 4th of July happening there, lots of fireworks. And in 1833, a new comet had gone by and left a lot of particles behind. So the first time we went through it, there were lots of particles there. Each time we go through it, there are fewer and fewer and fewer, as if it's in a place where we go around every year, which each of these are. So until the comet comes back around again and puts more particles, we'll get fewer and fewer each time. It'll be a smaller and smaller one. The Perseid meteor shower is one of the larger showers that we have right now. It's the leftovers of Comet Swift-Tuttle, and it is, in fact, something that can last for several days, and we get several streaks per hour from this. So it is actually a fairly strong one. Rocky Mountain High, if you've ever heard that song with John Denver, sort of, I've seen it raining fire in the sky. That's what it can look like, especially if you're up at high altitudes, because you have less atmosphere to interfere with what you're seeing there. Some meteorites are quite large, as you see here. This one is sort of interesting. We have this one land in an area. It was quote unquote discovered by someone who then promptly stole it and put it on display. Some things keep changing hands, sometimes legally, sometimes not along the way. But you can see how large this is, and notice it's iron. Remember last time when we talked about asteroids, that we can have the iron kind, we can have the metallic kind, we can have the carbonaceous kind, and we can have the silicate kind. If we've got the big iron kinds, they tend to leave a lot. If we go hunting for asteroid fragments, if we go hunting for meteorites, often if we go to places like Antarctica, or if we go to Greenland, or we go to places where there aren't a lot of rocks, just a lot of like snow and ice and not a lot else, and then we find all of this stuff here. Where did this stuff come from? Well, quite frequently it's come from above and landed here. So we have a more likely chance of finding meteorites excuse me, when we are looking at these different kinds of areas. Sometimes they will hit things in our society because we are spread around the world. So it'll hit trees, it'll hit buildings, it'll hit cars, it'll hit other kinds of things. I showed you an example of that last week as well. Here's some meteorite types. Again, we have the carbonaceous type here. We have an iron fragment here. Here we have a stony and iron mix with olivine crystals. Olivine can be interesting because sometimes olivine will trap water inside of it along the way. Here we have a bit of a meteorite that landed. People actually saw this land, so it was another way of provenancing that it came from above. And when we get these, we test them to see what's up. And especially if we get carbonaceous kinds, that excites people because we're looking for origins of life, possibilities that are there. Putting that together with the sort of ideas that we've talked about a little bit before in our semester, how things form. We were once a nebula. Remember, nebula is a Latin word for cloud of gas and dust. Collapses in under its own weight when it cools enough that the energy of each particle doesn't keep them apart. As they cool, gravity takes over, pulls them together. Most of the material goes to the center. 99% or more of the material in our solar system ended up in the sun. But everything has motion too. So as it forms, it flattens, but everything's also going in the same direction. And that's because when we're number one here, every particle is going every which way, but they bounce and hit each other. And as they slowly coalesce, as they accrete, remember that word, accrete, they join together or glom together. They're also hitting each other and they're regularizing their motions, and they end up pretty much going into the same direction. The nebula shrinks, everything becomes denser and denser. Most material concentrates near the center, but we have other areas where it gets clumpy, and those clumps will eventually turn into asteroids and comets and planets around the sun, but they've now regularized their rotation, because if they're going in any direction other than what everyone else is going, they're going to hit each other. And when they hit each other, gravity will typically hold them together. So we get larger and larger pieces. We call this the Nebular Hypothesis. It's one of two main ideas about how our solar system formed. The other is the Close Encounter Hypothesis. We'll talk a little bit about each one here in a moment. When we're looking at these theories, we have to account for certain things. Why does everything go in the same direction? And why is everything more or less in the same plane? We have all these asteroids and comets and other things out here, but in truth, that's less than 1/2 of 1%. 99.5% or more of everything in our solar system is in that same pancake plane. Why do we have two different types of planets? Why are there big ones out there and smaller ones close up? Why do we have the smaller things that are left over, like asteroids and comets? And why are certain things not the way other things are? Why is Uranus on its side? Why is Venus upside down in terms of their rotation? We'll talk about those in a moment. The Nebular Theory, again, nebula means cloud. If you look at the ideas of this a couple hundred years ago, you'll find some names like Immanuel Kant here. You would find his name mostly under philosophy, but he was also an astronomer. As we look at this, this is the number one idea, that we had that big gas cloud that collapsed down into our sun and planets forming together. Almost everything that we see out there supports this theory in it. The other theory that's going around is that our sun formed and we had another star that came very close. And as that other star came close to our sun, it pulled material off. And as it pulled material off, that stuff cooled into planets. That becomes more of a problem because it doesn't tell us exactly why everything would be going in the same direction. Although I could see how it could explain that, because if the star is going in that another direction, then everything's pretty much going in the same direction as that other star, and it happened to go in the same direction as our sun spins. So that's not a problem. But the types of planets, how do we get selectively what pulled off of the sun? Why isn't it all hydrogen and helium? Why don't we have things closer that are mostly made of hydrogen and helium like Jupiter? Why do we have very few things like the Earth way out? So it becomes trickier. But the nebular theory says we started out as a big cloud of gas and dust. Remember, we had this picture a long time ago in our earlier semester. 100,000 AUs. Remember, an AU is an astronomical unit, distance from the Earth to the sun. 100,000 is a lot because we're only 1 away from the sun. Jupiter is 5, Saturn is 10, Uranus is 20, Neptune is 30. So 100,000 is whoa. But this is only this little slice here. So if we're going all the way across the page here, we're at 1.5 million AUs. All of this will collapse down into the size of one of these dots here, because each of these dots is a star that used to be a nebula. And we can actually look out and see in different nebular areas, and I've shown you pictures that the Hubble's shown us from the Orion Nebula of different protostars and planetary systems forming. Stars form in gas and dust. They produce stars. The stars inside, as we'll see next week in particular, take hydrogen and turn it into helium, take helium and turn it into carbon, take carbon and turn it into higher and higher and higher elements. When it runs out of fuel, it will return that material out. If it's a large star, it will explode into a supernova. That material will cool off and then turn back into a nebula that collapses into a new star. We are all recycled stuff. You and me and everything on the planet, we're all stuff that used to be inside of stars sometime. So when we're looking at this, we can see in our Hubble images and our other telescopic images, stars that are forming, stars that are in their life cycle, and stars that are collapsing and exploding. And in fact, the most likely star to explode in your lifetime and my lifetime is Betelgeuse. So go out and pay attention to that one out there. What happens, of course, is we have gravity and we have electromagnetic energy, we have heat energy that's out there. These things are somewhat in tension with each other when we're forming a solar system because the heat tends to keep the particles away. They're energetic. Gravity pulls them together. But even after things have cooled, every particle has a little bit of temperature. And when they glom together, those temperatures add up and add up and add up. So at the center, where most things happen, it's going to be the hottest. The further away we get from the center, it's going to be cooler and cooler. So inside the solar system, it's hotter. Outside the solar system, it's cooler. And we have a line somewhere between the inner and outer solar system, which is called the frost line. Inside, everything will melt and evaporate. Outside, things stay frozen. And for us, that frost line is between Mars and Jupiter. Inside, here, Mercury, Venus, Earth, Mars, they are all rocky things. The rocks don't evaporate and boil away the way hydrogen gas and helium gas would. So here we're in closer to the sun, we're kept warm. But beyond this point here, we have the gas giants, Jupiter, Saturn, Uranus, Neptune. This is not to scale, by the way. This is just showing you the temperature drop. And notice as we're getting out here, we're getting close to absolute zero. So we're not at absolute zero, but we're close. When we look at some of the outer planets, we see they actually give off more heat than they get from the sun. And when we're looking at Saturn here, this is an infrared. So remember, infrared shows us heat signatures. These blue things, really, really cold, those are the snowballs that make up the rings. The rest of this here is the swirling gases inside, and that creates a little bit of friction, and that friction can generate heat. And so Saturn actually puts off twice as much heat as it gets from the sun. But as things form together, of course, everything was a gas and dust cloud. All the particles form together as they are cooling, and they collapse into a disk of material, which is still moving. All the motions keep going because we have conservation of momentum. We have conservation of energy. This is a basic physics principle. If you have two things that each have energy and they glom together, they have twice as much energy now for the one particle because the two things have put the things together. But that twice as much there equals the two halves that we had before along the way. You might lose a little bit in the bounce along the way, but that's still not losing the energy in the universe, it's just losing it to those two particles. So we do lose a little bit here and there, but since it's all in the same system, it just rebounds onto something else. So we have the gas and dust cloud that collapses more and more, gets denser and denser and denser. Of course, as it gets, we've got all of this stuff, the further out you're going, the slower you're going, the closer you're getting in and in and in and in. You're going faster and faster and faster. Think of an ice skater who pulls her arms in and goes really fast, and she puts her arms out and starts to slow down. Same principle applies here. As things are accreting, remember that word I mentioned before, everything's going around the sun. As it's going around, it's going around. They are glomming together until we end up with mostly the sun and a few major objects. We still have some minor ones, and it may sound like 150,000 asteroids is a lot of asteroids. We're talking, we started out with billions, maybe even trillions of them before. So that's actually not that much left over. In our solar system as it was forming, of course, the sun was in the center, all of our planetesimals going around, but we had another major center, which ended up being the planet Jupiter. Some stars out there have a twin star or a companion star. Our Jupiter area didn't have enough gas and dust to turn into another star, but it did turn into its own miniature solar system with some planetesimals around it that formed into moons. So we have a big system there. There would be yet another one out here smaller than this for Saturn. And as we look out at other stars that are in the process of forming, we often call these T Tauri stars, and you see Tau here is a part of Tauri. What we're seeing here is a star in the center with these areas that are dark. That's where the material's already beginning to accrete, already beginning to glom together and form into planets. So we can see this one's going to have 1, 2, 3 major planet areas at least, and probably several more along the way. So we can see what our solar system used to look like by looking at earlier ones. These are also from the Hubble, and I showed you these once before in a big collection of different items that are there. From the Orion Nebula, we're looking at this edge on. There's a star in the middle with all the gas and dust going around it and forming into a planetary system. This says is 17 times the size of our solar system. It will, of course, shrink as things go. This one here, the Beta Pictoris, we're looking at it edge on here. They've sort of blotted out the middle star so it doesn't obscure what we're seeing, but we're sort of seeing some energetic areas around. This is actually looking at the disk edge on so we can see things forming. And then over here, we also have our orbiting stuff. We see some companion stars. Remember, as I mentioned before, often stars will form in twins or even trios or more. And then we can see wispy areas where we've got clumpiness happening. So we have planets forming along the way. So as we look at these things, we can see the heat that is in the particles will also help us determine what kinds of planets form. As things form, if they're smaller, they run out of heat rather quickly and they tend to cool off, no activity. Like the moon and Mercury are basically cooled off geologically, they're done. Venus and Earth have a lot of material, so they still have a lot of heat trapped into them. They still have a lot of volcanic activity. Mars had volcanic activity more than Mercury or the moon because it's larger, but not nearly as much as Venus and the Earth. When we look at these three in particular, Mars, Venus, and Earth, we often think of Mars as the twin of the Earth, but not when we're looking at it like this. We can see Venus is much more like the twin of the Earth. Mars looks like us on the surface, but that similarity is in many ways only surface deep, only skin deep. When we're looking at things that are on the surface, notice here our largest mountains on Earth, Mauna Loa, part of Hawaii, part of that mountain, of course, is underwater. The Mount Everest peak in the Himalayas, in Asia, notice part of it is also below sea level. The Maxwell Mountains are on Venus, but look how large this is, Olympus Mons, on Mars. Why can Mars, which is, as we just saw, much smaller than Venus and Earth, have much higher mountains? The answer is, the smaller you are, the less gravity you have. The less gravity you have, the higher you can build. If you build much higher than Mount Everest on Earth, gravity pulls it all back down. Same is true for Venus. On Mars, you can build bigger, and it'll stay up there. This is Olympus Mons. It's probably this area here is about the size of the state of Missouri. This whole picture here would be about the size of Arizona. So this little dot here, which is actually a big impact crater, this one too, probably about the size of Phoenix and about the size of Tucson. This is a big place along the way. So when we're dealing with it, we're dealing with something that is ancient, but we're also dealing with something extinct. These craters would not be here if the volcanic activity was still happening. So it's cooled off. If you are even smaller than the moon, you often end up as an odd shape. We talked about this when we talked about asteroids before, how they don't have enough gravity to pull themselves together into a spherical shape. This is Ida, and we're sort of seeing all of these different views of it as we see it from different angles. So this is the long angle, this is a shorter angle along the way. And of course, Ida has a dactyl, which is a moon that goes around it. It's not being pictured here. We have some key exceptions to what's happening out there in our solar system, one of which being our big moon. Our big moon happened during the era of heavy bombardment. There were different theories about how the moon formed, and the primary one that we are mostly convinced, I'm going to say 90 to 95% convinced is the correct answer, is that when we had all of these different particles hitting each other and they got bigger and bigger, and I'm going to go back here for a moment to show you this one here. Notice we've got all these big chunks here. When these two big chunks hit, this is big, big stuff. And when it gets to this is even bigger and bigger and bigger. This we would call the era of heavy bombardment because there were big things hitting other things. We don't have big things hitting other things anymore in our solar system, so this is done. But at one point, we had things that were almost planet-sized stuff wandering, not in circular orbits through our solar system, and they would end up impacting the things that were going in mostly circular orbits. So we have some key evidence. The Caloris Basin in Mercury that hit so hard, it actually caused shock waves and fractured on the opposite side of the planet. This is the era of heavy bombardment. Our moon comes from that. We were probably hit by icy planetesimals. Some may be comets, some may be asteroids with H2O that created our water, and our atmosphere helps us to retain the water and helps to keep it in a liquid state. Some of these things weren't actually hit or didn't actually hit the planets, but they got captured by the gravity. Phobos and Deimos, as we mentioned before, are the two moons of Mars, and they are most likely captured asteroids. But our moon is not just a capture. Our moon comes from the era of heavy bombardment when we had these planet-sized things that were going around. And for our planet-sized thing, we actually call that Theia. And Theia is the goddess of destruction. It's one of the goddesses of destruction back then. So this was probably Mars-sized, maybe a little bit smaller than Mars-sized. And as our Earth is accreting and going around the sun, it's actually going around the sun too, but in a weirder orbit. It eventually hits us. And as it hits us, it shatters most of itself, and it shatters most of our crust as well. And we form this ring of debris. Our planet had a ring. But it also had a clump of the moon left over. Now there's at least one theory that it hit our planet, bounced off, and hit on the other side. So it actually hit twice. And the first time it shattered the outer crust, and the second time it shattered the inner core. But it had just enough of a clump left that after it bounced off and started going around us, it pulled material back towards it, hence the moon, but most of the stuff landed on the Earth. And that's partly explained by the fact that if you take a scoop of dirt from the moon and a scoop of dirt from the Earth, and you compare those two scoops, the one from the Earth, take away everything that has to do with water, life, or atmosphere, which they don't have on the moon, and the dirt is basically the same. So some minor differences here and there, but not much. So it tells us that we had this sort of common debris field origin that's there. There were a couple of other theories about how the moon might have formed. One is that our Earth was spinning enough it actually spun off the moon. That doesn't really explain how the moon doesn't have much of a core, however. It should have more of a core if it did that. Another is that we just captured it the way that Mars captured Phobos and Deimos. The problem is the dirt. You wouldn't have the scoops be about the same if it came from somewhere else. There would be much more difference there. So the giant impact and the Thea idea is probably the #1 idea that we follow now. And of course, my mother's name was Thea, and she loved the idea of being a earth-shattering, impacting device. So yeah, I'll go along with it. Now, when we look out at other stars, we have different planets that are going around them, and we know this now. But this has been an area of speculation for quite some time. In the earliest days of human history, we knew there were stars out there. We knew they were there before we could read and write. Up until the 1500s, 1600s, there was no real concept that the sun was a star. We take that for granted now, but back then, no. The sun was something different from the stars. Well, Christian Huygens, who lived in the generation after Galileo, we mentioned him before. Remember that backpack that was on Cassini that landed on Saturn's moon, Titan, named for Huygens here. He was a telescope inventor and refiner. He also had a photographic memory before there were photographs. We've only had photographs for about like 150 years or so. In astronomy, useful for astronomy, it hasn't been long. But Christian Huygens had a photographic memory, and he noticed if he went out and looked at the light coming off of a star and looked at the light coming off of the sun, he had this plate drilled with different sizes of holes. Don't try this at home. It's actually dangerous to do, but because you're not supposed to look directly at the sun. But what he did was he drilled different sizes of holes, and he would hold it up to the sun then. And he said, well, that looks like Sirius. That looks like Betelgeuse. That looks like Aldebaran. That looks like, and what he figured out was that it's the same light, but the sunlight is like very close. And stars are sunlight really far away. So he said, well, the sun is just a star up close, and the stars are suns far away. Well, if they're suns and they're far away, they might have planets. There were other thinkers back at this time who speculated on this as well. And one of them was named Giordano Bruno. Now, Giordano Bruno was a weird guy by almost any measure. And I don't mean that in an insulting way. He was the kind of weird guy that you go to see a TED Talk, or you go to see maybe even a comedy show. I often think of him in, excuse me, I often think of him in terms of maybe like a George Carlin and the different kinds of wacky kinds of comedians that are out there as well. When we're sort of talking about people who whack watermelons or do other kinds of things like that. Giordano Bruno might have been that kind of guy, but he was an intellectual. He was also a mystic. He had a lot of interesting ideas. He was actually invited to be a guest speaker around the time. They might say, oh, you've got to see this guy. He might have been like the Gallagher, the watermelon guy. And it's like, you don't want to sit too close. You don't know what's going to happen. But he had this idea that around other stars there might be planets. And of course, he was a Catholic, and he was a priest, a cleric. And he was under the authority of the church at the time. And the church said, of course, because he's speaking, he's supposed to get church approval. They said, yeah, we can buy that. There are planets around other stars, sure. He said, on those planets, there might be life. They're like, yeah, well, God's diversity, we have lots of stuff. And he said that life might have grown up into civilizations. And they're like, well, yeah, that sort of happens if you have life. And he said those civilizations might have other religions. Whoa. What do you mean other religions? No, burn him. And they burned him at the stake. Now, this wasn't the only idea they burned him at the stake for, but this certainly didn't help. And it sounds again like I'm picking on the Catholic Church, but in truth, if he had been in the Protestant areas, they were just as bad in terms of getting rid of people they didn't like. At this time, it was a pretty rough neighborhood on both sides of the tracks, and there was more political than theological issues going on at the time. Christian Huygens actually lived in the Netherlands, which at that time and in the present time still tends to be fairly diverse and open to different ideas. So he had these ideas, And one of the things he did was he figured out that these stars are so far away that our universe had to be much larger than we'd ever thought of before. Because if the stars were like the sun, you could do that parallax trick where you close one eye, put your thumb up, open your eye and see things jump, and they don't jump at all. In fact, none of the stars we have in the sky will do that kind of parallax jump with the naked eye observation, and only a few will do it even with our telescope observations along the way. But we now have other means of determining how far away they are. And we have other means now with the Hubble telescope, but also with a couple of different missions that are up there, past and present, that were specifically dedicated to looking for other planets. And perhaps one of the greatest ones is the Kepler mission. Of course, we remember Kepler as the guy who figured out everything going around in certain patterns around the sun. This is something that holds true in other solar systems as well, as we found. Lots of planets we've discovered are larger than the Earth. This is not because there are more of them. It's because they're easier to see. When you're looking for things, you're going to see the bigger things first before you see smaller things. So we see lots of larger than Earth-sized planets along the way. But we also see that there aren't too many that get that much larger than Jupiter. By the time we get 10 times the size of Jupiter or more, the number drops off quite a bit. There's a reason for that. Even though they're larger, by the time you get to be this big, you start turning into small stars. So instead of seeing planets, we're seeing stars. Here is a sort of chart of when we were discovering things. Notice this one here, 1995. This is the first verified exoplanet. We call them exoplanets when they're around other stars. Notice we've got a few dots before then. We had seen some things before then, but we didn't really know what we were thinking. We actually found something around a pulsar, and it turned out to be a planet around a pulsar. We had no idea this was even possible. We had a few other things that it turned out, hey, guess what? These are planets as well. But we hadn't figured out how to tell that those were planets yet until we discovered this one in 1995. But as soon as we figured out how to determine what we were seeing, guess what? We started finding them everywhere, everywhere, everywhere. And there are different ways of doing this. The main one is through indirect methods called sort of gravitational tugs and pulls, looking at the wobbles. But if we have direct evidence, we have a picture actually of it. We only have a handful of these. In fact, I think we're maybe up to 15. That may be too large of a number. Out of the thousands that we've seen, only about a dozen are seen in actual photographs. But mostly we discover things through indirect methods. As Jupiter, imagine this, if you're from the outside of our solar system and we are looking at our solar system from afar, we see the sun and we see Jupiter going around the sun, except they don't really operate that way. What happens, if you go all the way back to chapter 4, we talk about everything goes around each other. If you've got two things that are the same mass, they're going to go around each other with the center point between the two equidistant as they're both the same mass. Make this one larger and this one smaller. This one seems to go around this one, but this one's also moving around a bit, because again, they're going around that center of mass, which is now closer to the bigger object. Between Jupiter and the sun, the center of mass is not actually in the center of the sun. It's actually a little bit beyond the center of the sun. So as Jupiter goes around the sun, let's say my head is the sun and this is Jupiter. If Jupiter is over here, the sun is a little bit over here. By the time Jupiter gets over here, the sun's over here. So even if you can't see Jupiter, you might look at the sun, remember it's my head, going like this. It's wobbling back and forth. Now, Jupiter takes about 12 years to go around. So it's going to take 6, 12, 18, 24, 30, 36. It's going to be a very slow wobble that you're seeing if you're looking at it edge on. you're going to see this very slow wobble. So that takes a long time to figure out. That's part of why it took us a long time to figure out what's going on here. All of the planets actually tug and pull on the sun. It's just Jupiter is so much larger than all the others, it has the largest tug. So our center of mass of the sun actually shifts around. So we can actually measure that from here on Earth. This is called an astrometric technique. And these are very, very tiny. Remember, as we're looking at the sky, we're looking at 360 degrees. Each degree is 60 minutes. Each minute is 60 seconds. Here, we're not talking 1/10 or 1/100th. We're talking 1/1000th of a second, which is 1/60th of a minute, which is 1/60th of a degree, which is 1/360th of. This is a very, 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 very tiny amount that I'm getting at here. So we're actually able to measure these things very, very minutely. Also, as things are moving, they're giving off Doppler effects, as we talked about, I think, in chapter 5, when we talked about light. If things are moving towards you, it's giving it a little blue shift. There's a little kick in the light waves. If it's moving away from you, it's got a red shift. It's giving you a little bit of a tug. So while Jupiter, if we're watching the gravity shift, we'll sort of see Jupiter pulling on the sun back and forth like this. In fact, it's not going back and forth like this because Jupiter is going around. So that means sometimes Jupiter is going to be back here and the sun's going to be up here. And sometimes Jupiter is going to be here and the sun's going to be back here. So we're going to have it sometimes here and sometimes here. Blue shift and red shift and blue shift and red shift. Meanwhile, it's going back and forth like this. So in fact, the sun's going to be seeming to go like this. So when you see it tug back and forth, and then we've got a blue shift and a red shift and a back and a blue shift and a back and a red shift and a back and a blue shift. When we put those things together, in fact, we can tell there's something going around it. It's not even just wobbling back and forth. There's something going around it, even if we can't see that because the light from the star is obscuring it. So the first one we found was from just that way. And it's the 51st star in the constellation of Pegasus. That's why it's called 51 Pegasi. And unlike Jupiter that takes 12 years to just see one wobble, this one happens every 4 days. It's like, woo, yeah, that's really going there. Now, this is not unusual because Mercury goes around once every 88 days. We think that's fast for a planet. But when we look over at Jupiter, remember Jupiter has 3 big moons that go around in a pattern. There's a 4th moon that goes around that's also a big moon, but 3 goes around in a pattern. And Ganymede goes around once every 7 days. Europa goes around once every 3.5 days. And Io goes around in less than 2 days. So we've got evidence that things go around this fast. This is a planet that goes around its star every 4 days. So a year on this planet is in fact 4 Earth days. So that star is really, really, really wobbling. For a time before 1995, we wondered if there was something happening in the star quakes or other kinds of things, or maybe it was about to explode. Now we know it was a planet tugging back and forth. It's got to be very close to the star because, again, Kepler, thank you, the closer you are, the faster you go around. Further away you are, the slower you go around. And it's probably the size of Jupiter. So that ends up giving us some problems in terms of how planets operate, because if it's that close to the star, it should be boiling away. We call them hot Jupiters, and we're still studying why they're not boiling away, because we keep finding them over and over again. And some we find have cigar-shaped orbits. Some of them are a little bit off center and come closer. Some of them are pretty standard. Here we have sort of regular orbits here. We have massive planets that have odd orbits here. We have different kinds of eccentric orbits. That's what we say when we're talking about cigar-shaped orbits. Sometimes we're lucky enough to see things right edge on. Sometimes we're seeing things face on, so we can watch them go around like this. But most of the time, they're going to be at some kind of angle. Even when there's an angle, we can still see the star go back and forth, and we can still see it wobble back and forth. So we can measure those things. They give us lower limits on the masses when we do that. And some of our systems, we find more than one planet. Here at Kepler 11, we can see, again, the Kepler mission is a particular probe that was out in space. It's still in space, but it's not working now. That found we have 6 different planets going around. And when we're talking about these, notice the time of day here, or the time in days, sorry. We can see this one going around really, really fast. This one going around in less time. Almost all of these here are whipping around really, really fast. This is more like the moons of Jupiter going around in just a couple of days here with a planet A. It looks like it's going around once every 5 to 7 days along the way. When we're looking at our gray planet G here, we're only seeing it really once here. So we're not quite sure where that is. We see sometimes they line up and they block the sun quite a bit. This is using what's called the transit and eclipse method. If a planet goes in front of the star, and you can sort of see my backdrop here, if it goes in front of the star, it begins to block part of the light. And if it goes behind the star blocks the planet. So when we're looking at it, say we have here over here on the side, planet number 1, position 1 here. What's happening is we're getting light off of the planet coming at us, and we're getting light from the star coming at us. But as it goes into 2 and 3 here, notice we've got this drop. That's because it's blocking part of the star. We're also seeing the dark side of the planet, so we're not getting any light from the planet. It's sort of the new phase. As it goes past over here into 4, we're again seeing the light from the planet, so the light curve goes back up, and the full star. When it goes behind the star, we're no longer seeing the planet, but we're seeing the whole star. Nothing's in front of it. So when we have this double dip, but one dip is lower than the other, we know there's something going in front of it sometimes and behind it in the other. So when it goes in front, we call it a transit. When it goes behind, we call it an eclipse. If we get really lucky and this planet has an atmosphere, the light as it goes past the planet, but through the atmosphere, we can measure what we saw in the star before the planet was in front of it, and what we're measuring now with the planet in front of the star. And if we see, okay, there was no carbon here, but now there's carbon, there was no water here, but now there's water, we can tell that's part of the atmosphere of that planet. And that's why every now and then you'll hear we have an Earth-like planet with atmosphere, with water, other kinds of things like that. And it was really the Kepler mission that operated for about 10 years, and it fell apart at one point, and NASA engineers were so clever that even from Earth, they were able to reorient it and change it around and rework it from a distance without actually having to put their hands on anything, so that they could get it back up and running again. It really did great work. And what it was doing was it was measuring the dip in the brightness of the stars. So if something went in front and went behind and went in front and went behind, that means if anything's at an angle, it's not going to see. Kepler couldn't see anything at an angle or anything that's going around face on. It could only look at things if they were edge on. But it was able to analyze tens of thousands of planets. And not all of them have been verified yet, but it'll probably be at least another 10 years of material that we have from Kepler as we're continuing to look for other planets that are out there. We have other missions that are out there now. We have a Gaia mission. We have terrestrial planet hunter missions. If you've been looking at some of the different things on Zooniverse, you may notice that there's some data sets that are given to you in those projects that deal with the terrestrial planet hunters, and those are still ongoing. So Kepler really opened the door, and it did a great service to us, and it will always be in the history of early space astronomy one of the key instruments that we've had out there. It'll rank up there in the future when people are thinking about things. Hubble and the Kepler and the Spitzer and a few others that are out there. There will be a handful of them, but those, I would say those are going to be 3 of the big ones that are there in terms of what we put into orbit to look at the rest of the universe. So here we go. If you're still looking for a final project, looking for things about exoplanets would be a good choice. Looking at the Kepler mission would be a good choice. Looking at the Spitzer mission would be a good choice. So there are all sorts of possibilities that are out there for your final project. Let me stop our share here so you can see me in sort of all of my glory. Again, the backdrop that I'm showing you here, what we see here is a transit and eclipse. If you were standing on the moon, if we were sort of sitting here where we are and sort of turn around and look at the sun, what's happening, of course, is the Earth is going in front of the sun. And we call that an eclipse. Technically, it's a transit. As it's going, it's eclipsing the sun, but as it's going across, the Earth itself is transiting the sun. Every now and then we see Venus going across the face of the sun, and if it goes across the face of the sun, it's just a little tiny dot that goes across. We can sometimes see Mercury doing that too. It's an even smaller dot that does that. But if we're on the Earth, we see the moon do that, and it covers the sun completely. We call that an eclipse because it's eclipsing the sun, but in fact it's a transit. So we play around with those kinds of wording along the way. We have to get really lucky. Notice how small all these stars are out here. We have to get really lucky to get things edge on. So even though Kepler saw tens of thousands of stars that were like this, there are billions and billions of stars that are out there that are going to be at other angles, and we're not going to be able to see the transit and eclipse method from here on Earth. So we have other missions that look for other things like the wobbles and other kinds of methods of exoplanet detection. When I was taking this class in 1982, 83, well, there was one sentence in our textbook that said, we don't know of any other planets around any other stars, but maybe someday we will discover some. We had no idea. We had no idea. Now our idea is that every star has a companion star or planets, or in fact, both. For a while, and this sort of shows what happens when we're dealing with science, after we've discovered 51 Pegasi in 1995, there was the idea that, okay, there are planets going around other stars, but if you got two stars going around each other, a binary star, or three stars, a trinary star going around each other, that's never going to work because the stars going around, they're going to throw all the planets out. The gravity is going to push all the planets out. Until, hey, we discovered a planet going around multiple stars. And it was in a stable orbit going around multiple stars. It wasn't being tugged and pulled in weird ways. It was perfectly stable. Now, those of us who grew up in the 1970s knew there's no problem with this because we remembered Star Wars. So a long time ago in a galaxy far, far away, Luke Skywalker walked outside after being told he couldn't go to Starfleet Academy and put his foot up on this regenerator and looked up, sort of up to the sky like, why is this happening? And there were multiple stars that were setting. It was a sunset, but there were multiple suns setting. And of course, he was standing on the planet Tatooine. So that was 1977. When we discovered that planet going around multiple stars, they named it Tatooine. And with that, I will let you go, and I will see you next week.